Hey everyone, so today we are going to talk about Cayley Hamilton Theorem, one of the very important and nice and simple theorem in linear algebra. Okay, so it says that if you have a square matrix, say of order n cross n matrix, then that matrix will always satisfy its characteristic equation. That means what? So once you have a matrix A, first thing you do is you find this characteristic equation. How do you find the characteristic equation? Determinant of A minus lambda I. When you solve this, you get a polynomial in lambda, which we call it as a characteristic polynomial. And when you equate it to 0, it's an equation, so we call it as a characteristic equation. So this is something in terms of lambda. So let me call P of lambda equal to 0. So this is your characteristic equation for the given matrix. Then Cayley Hamilton proved that your matrix will satisfy this equation. That means what? When you replace your lambda by A, then this is equal to the zero matrix of order n. So when you replace your lambdas by A, so on the left hand side you will have a matrix, right hand side is nothing but the zero matrix. So that's what these people proved. And this is very nice. This has very nice applications in problem solving. So I will take an example and I will try to explain you its application with the help of an example. So it will be easy for you to understand. So suppose this is the 3 cross 3 matrix you have 2 minus 1 2 minus 1 2 minus 1 1 minus 1 2. The first thing is you find the characteristic polynomial P of lambda, which is determinant of A minus lambda I, and when you solve this, this is what the answer you get. I have just written it directly so as to save your time. So this is what we have. So what is the characteristic equation? This is equal to 0. Lambda cube minus 6 lambda square plus 8 lambda plus 3 equal to 0. So by Cayley Hamilton theorem, every matrix satisfies its characteristic polynomial. That means what? Here you will have A cube minus 6A square plus 8A. You replace your lambdas by A. This is 3 means 3 into 1. You replace your 1 by the identity matrix is equal to the 0 matrix of order n. Here it is the 0 real number and here it is a 0 matrix. Okay, here it is 3 into 1. 1 is a number, real number. Here it is 3 into identity matrix. So this is what we have. Okay, if you don't trust them, then you can simply find this value. You have A, you find A square, find A cube, plug in on the left hand side, your answer will definitely come out to be 0. Okay, so this is what we have by Cayley Hamilton theorem. Now suppose the determinant of A is non-zero. That means suppose A is an invertible matrix. Then you know how to find the inverse. Like you can use row operation, column operations. Then you can also go by adjoint method. So you can use those methods to find the inverse. Well, you can use this method as well to find the inverse. So what to do is you keep this identity on one side. Oh sorry, this is minus 3 over here. Yeah, so you always take the identity term on the other side. So what you have, 3 times identity is equal to A cube minus 6A square plus 8A. Now you multiply by A inverse. So 3 into A inverse is nothing but this will be A square minus 6A plus 8I, because A cube into A inverse is A square into A inverse is A into A inverse is identity matrix. And therefore what is your A inverse? It is 1 by 3 times A square minus 2 times A plus 8 by 3 times the identity matrix. So if you want to find the inverse, you know identity matrix, A is given to you, you find A square, simply plug in the value, you get A inverse. So that's quite simple, right? Finding A square is not that difficult. You simply find A square, plug in the value, you get A inverse. That is the first observation. Second remark, if you observe carefully, this theorem helps you to write inverse of a matrix as a combination of powers of the matrix of A. This is A raised to 0, which is identity, A raised to 1 and A square, and the scalars over here. So this theorem helps you to write inverse of a matrix as a combination of powers of the matrix of A, and that too good powers, like this is 3 cross 3. So the powers will be A square, A and A raised to 0. If you have say 4 cross 4 matrix, In that scenario, your A inverse would be combination of A cube, A square, A and identity. So one power less. So if you have a 10 cross 10 matrix, then you can write, and if it is invertible, then you can write A inverse as combination of, I said 10 cross 10, right? Yeah, so for 10 cross 10, you can write A inverse as combination of A raised to 9, A raised to 8, A raised to 7 up to identity. So you can always do that for a square matrix which is invertible using Cayley Hamilton theorem. So that's the second observation or second remark. Good. So we can write them in the combination, or we can actually put and we can find the values. What are the other benefits of Cayley Hamilton theorem? Another important use of Cayley Hamilton theorem is you can find the higher power of the matrix. Like this was a 3 cross 3 matrix, right? So here you can observe, you can write A cube as 6A square minus 8A plus 3I. So you can express the cube of the matrix as a combination of smaller powers of A. So A cube can be written as combination of smaller powers of A. So A raised to 0, A raised to 1, A square. Not only A cube, you take any power which is greater than 3, greater equal 3. Like if I take A raised to 4. So if I multiply both sides by A, I have A raised to 4, 6A cube minus 8A square plus 3A. But what is my A cube? By this part, my A cube is nothing but 6A square minus 8A plus 3I. And here minus 8A square plus 3A. And what is this? This is 36A square. And 36 minus 8 is how much? 28A square. 8 6 are 48. Minus 48 plus 3 is minus 45A. And 6 3 are 18. So not only A cube, you can also write A4 as a combination of A square, A and I. Similarly, you can write A raised to 5. So multiply by A again. So it is 28A cube minus 45A square plus 18A. Then this is 28. Again you put the value of A cube over here. So again A raised to 5 also can be written as the combination of powers of A, combination of A square, A and identity. So whenever you have a 3 cross 3 matrix, you take A raised to k, where k is greater or equal 3. It is nothing but some number times A square plus some number times A plus some number times identity. So you take A cube, A raised to 4, A raised to 5, A raised to 6 and so on. You take any power of A. Since it's a 3 cross 3 matrix, you can write them in this way for some scalars C1, C2, C3. If it is suppose 4 cross 4 matrix, then you take any k greater or equal 4, it can be written as combination of A cube, A square, A and identity. Any power greater or equal 4 can be doable in that way. So that's the another strong point of Cayley Hamilton theorem, that if you have a matrix of order n cross n, then you take any power of A which is greater or equal n, that can be written as combination of A raised to n minus 1, A raised to n minus 2, A raised to n minus 3 up to identity. You can always do that. And that's a very good thing, right? Because we know that as the matrix becomes large and large, for example 1000 cross 1000, billion cross billion, crores, trillion cross trillion, then it's difficult to find the powers of a matrix. But thanks to this theorem, we know that power is some combination of the lower powers. So that's another important use of Cayley Hamilton theorem. Now one last problem. So you have a 2 cross 2 matrix. You find the characteristic polynomial. So this is by Cayley Hamilton theorem. It satisfies, the matrix satisfies the characteristic equation. Your job is to find this value. Now one way is you find A square, A cube, A raised to 4, A raised to 5, plug in and you do. But that's not the efficient way, even you know that. So what is the other way? Like other way we saw earlier. Once I have this, I know A square is some A times plus something times I. Then A cube also is something times A and something times I. Similarly, A raised to 4 and A raised to 5 are something times A and plus something times I. So you can do that till A raised to 5 and then plug in everything over here and you can simplify. That is second method. Third method, you can actually do the division algorithm thing. You divide this by this, or you divide this by this. So A square minus 4A plus 3I, you divide to this. A raised to 5 minus 4A4 minus 3A cube plus 2a square minus a plus I. Now here you can see you multiply by a cube. So this is a raised to 5 minus 4a raised to 4 plus 3a cube. And then you subtract, right? So when you subtract, this goes away, this goes away. This is minus 6a cube plus 2a square minus a. Now you multiply by minus 6a. So again this will be minus 6a cube. This will be 24a square and this will be 18a. Again you subtract. So this goes away. This is minus 22a square and this is 17a plus I. Right? And when now you multiply by minus 22 into identity matrix. So what you get is minus 22a square. This is 88a and 66i. When you subtract, this goes away. 88 minus 17, it will come out to be 71a, and this is 67i. So what is a dividend? This is a dividend, right? So your dividend, which is the given question, your dividend is equal to quotient into divisor. But I know that what is divisor? Divisor is equal to 0. So it is quotient into divisor, which is 0, plus the remainder 71a plus 67i. So this quantity is nothing but 71 times the A matrix plus 67 times the identity matrix. So you can use this division algorithm as well to find such a big expression. So yeah, that's about Cayley Hamilton theorem. One can talk much more things, but yeah, as if now I will stop over here. If you have any other doubt or any other problem which is not doable by you, you can ask me in the comment section. I will try to help you. And if everything is clear, then yes, do not forget to like, share and subscribe. Thank you.